All right, so we're looking at titration, and usually we use titration as a means of determining the concentration of an unknown solution. And so we're gonna walk through this question and see how best we can utilize what we know in terms of moles and concentration and titration, neutralization, acids and base, and see how we can answer. So it says to determine the concentration as I said, once we're doing titration, usually the aim is to determine the concentration of an unknown substance. And to do that, we use a concentration of a substance that we know. So of a solution of sulfuric acid, what's the formula for sulfuric acid?
H2SO4.
All right. And just for purposes, what type of acid is sulfuric acid? Is it a dibasic, a tribasic, or a monobasic acid?
Diabetes.
So dibasic, do you understand why we call it a dibasic?
Um, well, I only I remember now, but I can't really remember right now. It's something about there's only two something something in the solution, something like that. I don't
So
remember.
2 something something.
Mm-hmm.
So for every 1 mole of this acid, it is capable of providing 2 ions of the hydrogen, right? So
Yeah.
Paul, we don't know about Paul. Is Paul from the Bible? So maybe we can ask him where's Mark, Luke, and John. So
Jesus.
Paul titrates the acid against a 25 centimeter cube portion of a sodium hydroxide solution of concentration 8.0 grams per dm cube, using a suitable indicator to identify the neutralization point. And it says here are the burette readings. So let's talk a little bit. For titration, we would use a pipette, and in this case, a pipette that measures 25 centimeter cubes, and we will pipette that 25 into a conical flask. Now, we would also allow and this is for the sodium hydroxide. What is the formula for sodium hydroxide?
NaOH.
And so solution, we did mention in terms of concentration that it is 8 grams per dm cube. So I just ask you, what is it for sodium hydroxide? You say NaOH. And we were talking a little bit about, we pipette in, so we use a pipette to get the 25 centimeter cubes of the sodium hydroxide. And so the pipettes are basically designed to get that accurate portion of the solution. Now, this is the one that we know the concentration of. And the question provided the concentration in grams per dm cube. Remember, concentration is in 2 units. Either you have mole per dm cube or grams per dm cube. So let me just deduce what this is saying. in 1000 centimeter cube, that will contain basically 8.0 grams of the sodium hydroxide. So that's the amount that was dissolved in a 1000 centimeter cube or 1 dm cube volumetric flask to obtain that standard solution. And out of that solution, you would have pipetted 25 centimeter cubes to use as in your titration. Now in your burette, that is where you place your unknown. So we wanted to know the concentration of the sulfuric acid. So in the first case, what we would have done, and if you notice how the readings are,
Wait, sir. Yes, just showing something. No.
1 second. Yes, I would be showing something. So we would have had, these are the readings. Sorry about this line. So the readings that we have, when we look from this, remember we read it from the top to the bottom and not upwards for the burette. So before, and we have the after. What's the before? Based on this reading, we want to zoom in. So what's that before?
Um.
So right here.
Isn't that?
And we said that we read the burette from the top. So 0 is here.
Oh.
So read in this direction.
Okay.
So 0 to 1, that direction.
0.5. 0.5.
So definitely 0.5. And then when we look at after,
15.3.
how much?
15.3.
So 15.3. Look at my tree.
Boy. Sir, wait. You said the unknown substance is in the burette. That's it?
Yes. Because see here to determine because what you would always do is to use the pipette. You pipette the 25 centimeter cube, in this case, of the solution that you know the concentration, which was the sodium hydroxide. So it is actually the sulfuric acid that you don't know the concentration of is placed in the burette. So as I said, 15.3. Well, you said, what is this before? The second time we did it, or the second time Paul did it?
1.9.
So 1.9 and
16.6.
in this case
4.2.
and here
and 18.4. Wait.
18.4.
Wait. wait. No.
Remember
18.9.
Definitely. All right, so let me reduce the size. It's a little bit back. All right, so it says, name the piece of apparatus Paul would use to measure his 25 centimeter cube portion of the sodium hydroxide. What did we say he would use to measure that?
The pipette.
The
Pipette.
So the pipette. So you'll use the pipette, and not just any pipette, but a pipette that would measure out the 25. Because as we said, we would have different pipettes allowed to measure out the precise volume of a solution based on its capacity.
Oh, so is there like a specific name for those, or it's just
No,
called
as
a
in we call it, we just saying a 25 because that is the amount that we want to get. So you have it being named based on the volume that it can pipette.
Okay.
But in general, most of them in our context of the CXC chemistry, or when you're doing titration in our line, we would use a 25 centimeter cube. But you do have other volumes out there in terms of the pipette. It says, what do you understand by the term neutralization point? No.
Neutralization. Oh, okay.
All right, go ahead.
No, not at all. Okay, wait. All right. Neut- yeah. All right. Never mind. Because it's probably not on me. I think so. Never mind.
All right, so we know neutralization is when you have a situation of a acid reacting with an alkali. And that is primarily what we see happening up there. We have sulfuric acid reacting with sodium hydroxide. Now the neutralization point would have been the point at which you have a situation where, and let's go back to acids and alkali. We know that the sodium hydroxide, one of the things that it will be doing is to provide the OH. One of the things that the acid would be doing is to provide the H plus. And in a neutralization reaction, you have a salt forming along with water. Now, the neutralization point is the point at which you basically don't have differences in these two ions. So none of them is more than the other. And so it's like an equilibrium point, basically, where the same, there's no, it's not a situation where you have more H plus ions more than your OH ions. Cool? So we want to get that in focus. Says none of these ions would be in excess of each other. So they're basically at a point where they're equal. So that's the neutralization point. Name a suitable indicator Paul could use to determine the neutralization point. So the neutralization point, some of the indicators that we use include, of course, the popular phenolphthalein. So phenolphthalein is one of the indicators we can use.
Orange one.
So the methyl orange is another indicator. Also, the screen methyl orange can also be utilized. So any one of those we can use to identify. And one of the things that you're looking for is that color change. So when you think about placing the indicator, you'll be placing the indicator in in the alkali. And so if you're using a particular indicator, they will provide a color. And so you look for that color change to note the endpoint or the neutralization point of that reaction. Now, back to the readings that we obtain.
Wait, sir. So so when the indicator is being mixed, well, no, it's being poured into it, and you start like swirling it, right? So you wait until it turn like a permanent color, and then that would have been the reading.
So depending on what you put, say for example, phenolphthalein, it depends on which one you place it in. So the phenolphthalein would be pink in the base or the alkali. And so the OH will be reacting with the phenolphthalein and providing that pink appearance. So when you start to release the acid within the base, you know you're going to have those reacting, forming the salt and the water. So the moment the acid now have that point where it reacts with the last, OH ion, then you're looking for that point, and that's one of the reasons why you have to be monitoring. And when you reach to the close to the point, you actually add, in this case, the acid drop-wise, because you want to see when that one drop changes the solution to know the neutralization point. So as soon as you have just an excess of hydrogen over the OH, then the solution will turn clear. So it's moving from pink to clear. So even Paul, that is what he would be looking for in this experiment, where as he adds the acid to the base or the alkali, at that point where you have that pink appearance turn into clear, signals the neutralization point, the point that you have, as we said, now you may have a little bit of hydrogen ions that would have been there because all of them would have now been used up to create that water. And so because you don't have any more, the phenolphthalein doesn't have anything to react with to have that pink appearance. And so it turns clear. Now, in terms of the reading, what did we say? The initial reading for this, if my memory serves me right, would have been 0.5.
Yeah.
And I think this was 15.3. Did you write them down?
Nope.
So we subtract the initial from the final, and we would have gotten, this would have been what? 14.7.
So you have to subtract it to find the volume.
Of the
The volume of acid
acid
added. Okay.
used. So we want to find the volume of the acid used. So we take away, because this is the start point, and this is showing you how much of the acid. This is how we determine how much of the acid that was used to neutralize, right, the alkali, the sodium hydroxide. And of course, we repeat a titration to try and obtain a more accurate. And by right, we should have results that are at a 0.1 difference. So we should actually do our titration until we get a 0.1 difference.
Oh, okay.
So what were the other reading? So just remember these reading. We said 1.9.
Wait, sir, that was cool. May I take a picture? Okay.
All right. So you can, so we said this was 1.9 and the final was, what was the final?
16.6.
And so how much is this again?
Whoa. Oh, 14.7. Okay, okay.
No, for the third attempt, and as we said, we would have, sometimes what we do or what we see is a rough. And persons will ask me, or students will ask, do we utilize the rough? Sometimes we
Mm-hmm.
can, dependent, as I said before, if it is that the rough gives you a 0.1 difference. Say for example, you had a rough here and the result of that rough is close, a 0.1 difference to the volumes that we're getting here, and maybe even the the titration 3 values were out. We can use the rough 1, 2, and not the 3 to get the average volume that we would have wanted to use, or determine the volume that we should use. So in this case, Paul, for the third time he did it, what was the initial?
4.2.
4.2. And what was the final?
18.9.
So
And that,
again,
yeah, 14.7.
and we're seeing normally in Paula works on miracles, man. Because normally, with human error, you have to be very keen in ensuring that you don't go over. And so you have to do it drop wise. So it's very accurate. Paul works on miracles. The next question says, determine the volume of sulfuric acid needed to neutralize the 25 centimeter cube of sodium hydroxide solution. And so what you would do in this case is to add.
Oh, all three of them.
Yes.
Okay.
And then because you're doing the average, we basically would divide by 3. And if
3.
you're looking and seeing the math technically, we're saying that it is 14.7 centimeter cube. What
Yep.
does this mean? In terms of reaching the neutralization point, remember we had 25 centimeter cube of the sodium hydroxide. And so to neutralize this, we needed 14.7 centimeter
14.7.
cube of the sulfuric acid.
Okay. So whenever there's a question like that, it would have been asking you to find the volume of the acid added and you find the average. Well,
Definitely.
not really add, but find the average. I mean, like,
Yes.
yeah.
So one of the
Oh.
things that CXE might do, in this case, I've seen them do it on papers. They may ask you to specify in terms of a decimal place. So they will do that. Sometimes they ask you, or you're given the results. After you do your results, they may ask you to tick the titration that you would actually use. And so you need to remember about that closeness in terms of the zero point 0.1 value. Because as I said, if you're not at that 0.1, you might not want to use that. Titration is something that is, you want it to be precise as best as
Mhm.
possible. So
Alright.
anything outside of a zero point 0.1 difference, we wouldn't be using it. Now it says calculate the number of moles. Calculate the number of moles of sodium hydroxide used in the titration. Calculate the number of moles. Now we know, and if we can recall, let's go back to the question. The question is there to guide us. So let's look back. When we spoke about, if you notice right here, they would have given you the concentration, and this, as I said before, is in mass. So there are two approaches that you can actually, there's
Oh.
two approaches that you can take. You can either work out the moles per dm cube,
Mm-hmm.
and then you find out how much is in the 25 centimeter cube, or you can use this 8.0 grams dm cube and find out how much grams is in the 25, and then you convert that to moles. So I'm going to do it using the last method.
Same.
I'm not sure if I have space. Probably we can do it using both methods just to show you that it will work out. So as I said before, since I have, this is what I know.
Mm-hmm.
In my 1000 centimeter cube, because that's what concentration means, how much is in 1000 centimeter cube, or how much is in 1 dm cube, and how much that was
0.8.
grams. And so I can find out how much grams is now in the 25 centimeter cube. And as you know, this is your conversion factor right here. And so it's 25 times. And if I have centimeter cube right there, whatever unit I have here, I put it as the denominator. Centimeter cube. And I have 8 grams. So now, this will provide me with how much grams is in the 25 centimeter cube. So work this out for me. As you know, this would have been 25 times what? 0.008?
Of 0.2 moles.
0.2 can be moles.
Gram?
Yes, it here grams.
Grams. Oh, yes, yes, grams are true.
So I now know that in my 25, and it makes sense, because if I make the standard solution and I place and I utilize 8 grams to make it. If I take out 25 centimeter cube, right, it would have way less in terms of the mass of the sodium hydroxide. Now, in this case, we're saying that in 25 centimeter cube, I have 0.2 grams. Now, again, here's the thing. Even in this question, they provided you with the atomic mass of the elements. And I want you to link back this. I've been saying this to students. The moment you see a metal, it simply means you're dealing with a ionic compound. Because a covalent compound will not have a metal in it. Now, also, we want to talk about the relationship because it did say calculate the number of moles. And since there's a relationship here, we have mass, we need to get to moles. We know that 1 mole is equal to the formula mass. And we learn this when we're doing the mass to moles and the moles to mass. So we're applying. Now again, as I wanted to point out, if you finish this question and you didn't use these, then something is wrong because it did provide them for a particular reason. They know that you would have needed them. So when you think about sodium hydroxide, we have sodium, and if you can recall it, the formula, one of the things that is a problem to students, and I don't think once you're doing acids and base and, we should get familiar with this. This is a popular alkalis that we utilize. So in the formula, we only have 1 sodium. Each sodium has a mass of 23. We have 1 oxygen, that's 16. We also have 1 hydrogen, which is 1. So technically, it is the 23 plus 16 plus 1. Which gives us
40.
So we know if I have a mole of sodium hydroxide, it's basically going to weigh 40 grams. Now, again, I have my conversion here, but I didn't have 40 grams. I had 0.2 grams, which means I'm going to be multiplying that. I'm going to create a fraction from this, whatever unit that is here, place as the denominator over the 1 mole. And so technically, again, sometimes students are not sure why they cross multiplying. This is not 0.2 times 40. It is actually 0.2 times 1, which is 1 times any number is the same number. So technically, we should have 0.2 divided by 40. That would give us our answer in mole.
So when I do that now, it's giving me in particles on my calculator.
So there's a button that you can press to provide it in. It's not giving you in particles. So what is the number you're seeing?
5 times 10 to negative 3.
So 5 times 10 to the negative 3, you should be able to read that. So it simply means that it's 0.005 moles.
That's what it means? Okay.
So yes, that's what it means. So if you would have the moles. So we now know that 0.2 grams in moles is 0.005. So you would have seen something on your calculator, as I said, looking like this. Why my trees are looking so? So you basically know that you bring the decimal place 3 places, right, to the left. So this is actually how we end up with that. Now it says write a balance equation for the reaction. So again, what is it that we know? We know that all acids are aqueous.
What did you say, sir?
See if I can erase this thing. All right. So all acids are aqueous. And the alkali, all the alkali are also aqueous. Now remember, this is an acid and base reaction, also known as a neutralization reaction. In a neutralization reaction, we get a salt and water. So the metal from the base or the alkali will replace that of the hydrogen in the acid. A matter of fact, the question could have leaned to, because we're doing titration, you may not see that, but we could talk about acid salt. So an acid salt can be formed from this sulfuric acid, because right here it's a dibasic. So the sodium could only replace one of the hydrogen. So you'd have sodium hydrogen sulfate as the acid salt. So an acid salt is created when not all of the hydrogens are replaced by the metal. So that could have been another twist or another question that they could have asked. Show the balance equation to form the acid salt, and show the balance equation to show a normal salt. So we're working with the normal salt. So we know that the sodium is going to replace the hydrogen.
Mm-hmm.
And so remember
And then, yeah.
that what you want to keep in mind is the ions that are used to formulate the compound. So the Na plus and the SO4 2 minus, that is how we get to this. So a lot of times, students may make a mistake and write NaSO4. We have to be careful of that. Also, we said that we would have obtained water.
Mm-hmm.
And so we look at this, right? And we recognize that, I'm not even going to go into the detail of how, but we recognize that we have 2 sodium. If you're in the exam, you can go my route of tallying. You do your inventory of all the elements or the ions. In this case, if we are seeing the polyatomic ion on both sides, the sulfate, we treat it like an element. So we know that we need to get this sodium. We have 1 sodium on this side, 2 sodium on the product side, and we want to get 2 on this side. So we put a coefficient of 2. But by doing that, it also changes that of the O and the H. And if you're asking why we started with the sodium and not with the hydrogen, usually when we're balancing, the little rule that we want to remember is that we start with, or we leave hydrogen second from last. You know, in a Jamaican terms, we say second to last.
Mm-hmm.
And we leave oxygen for last. So technically we would start with the sodium, and by doing so, everything else should fall into place. So when we look at this, the 2 hydrogen, and we also have 2 hydrogens here, so we need 4 hydrogens on this side as well. So we would have put a 2 here. Also, if you notice, for here, we would have had 2 oxygen. We have 2 oxygen. We're not going to be talking about the oxygens that are in the sulfate because we're treating that like an element. So we have 1 sulfate here, 1 sulfate here. And so this would have been your balanced chemical equation.
Right.
Now, whenever you are doing titration, one of the things that is going to be helping you is moles in chemical equation. So we just want to talk a little bit about that. Now, the sulfuric acid, if we're not seeing a coefficient in front of any compound in a chemical reaction, we know that there's a 1. So we're not seeing any in front of this, there's a 1. So you need to understand that we have 1 mole of sulfuric acid reacting with 2 moles of sodium hydroxide. This will provide 1 mole of sodium sulfate and 2 moles of water. And so the questions will be related to, because in this case, we're really zeroing in on the reaction that is happening between the sulfuric acid and the sodium hydroxide. So if you take this for example, the ratio is that every 1 mole of sulfuric acid, you're able to react it with 2 moles. So it's a 1 to 2 ratio. So every time you have 1 mole of this, you have 2 moles of that. Which brings us to something that, and they're going to be asking us, but you can look at it. So if I have a point, and this represents the moles of sodium hydroxide. So I have 2 moles of this in this case. So when I have 0.005, we should know that we would have had basically, technically, a half of that for the sulfuric acid because it's a 1 to 2 ratio. So if I have 2, then I have 1. So if I have 0.005, I have half of that for the sulfuric acid. But I'm going to be showing you how to work that in detail just the same. So it says now, determine the number of moles of sulfuric acid using the titration. So that's where we're going to be using the mole ratio that I spoke about. So we know 1 mole of H2SO4 is equal to 2 moles of sodium hydroxide. And so students always, sometimes complain about the length of what I do, but it kind of eliminates. So again, I get my conversion. Once I get my conversion, I know how to work it, because I know that I'm starting with 0 or 0.005 moles of sodium hydroxide. So in essence, I'm going to be multiplying that. And again, we're going to be seeing it. So if I have moles of sodium hydroxide, I did say whenever you get your conversion, whatever unit that is here, that forms your denominator in your fraction. So the 2 moles, I'll leave off my M, of sodium hydroxide over the 1 mole of sulfuric acid. Then, of course, we now see it. This mole of sodium hydroxide cancels out this mole of sodium hydroxide, leaving our answer in moles of sulfuric acid. And that's what we want. We were asked to determine the number of moles of sulfuric acid used in the titration. Now, here's another thing. Same as how I said it. So really and truly, we're seeing a 1 to 2, so we know that it is half. See, come back right to us here. So technically, we are dividing by 2. Which is?
0.1.
That's what we get.
Alright, wait, I'm gonna check it out with it. I'm gonna check it out with it. Wait, hold on.
Tell us the original number that you get.
Sir, it's 2.5 times 10 to negative 3.
So 2.5 times 10 to the negative 3. And like I said, you need to learn that we're bringing the decimal place 3 places to the left.
What is the thing to convert this on this calculator?
I'd have to look on the calculator to tell you. So I'll sort that out. Or you can always check with your physics teacher or a math teacher. Just go to the math teacher, because that is something you need to sort out if it's giving you a problem before you go into the exam. Because simple things like that. So really and truly, but if you're seeing that negative sign, 10 to the negative 3, all we're saying is that we move the decimal places to the left 3 times. So we would have ended up with 0.002, sorry, 0.025 moles. And this is moles of sulfuric acid. And so with titration, if you notice, for each question, and this is how it always is at times, you need to answer the question, because whatever answer you get will be needed to move to take it to the next.
So it's 2 zeros, right? 2 zeros.
Okay. So 0.00, because we're bringing it to the left.
Okay.
So it says, watch what they did now. They are asking us for the molar concentration. Once you see molar concentration, what is it that they want? Once you see concentration, we want to know how much mole is in 1,000. centimeter cube. But this 0.002 moles is in how much? That would have been linking back to what we use, the volume that we use in our experiment. So that would have been 0 or 0.0025 moles would be in 14.7 centimeter cube. And as we said, they ask us to determine the molar concentration. So we want to know how much is in 1000 centimeter cube. And again, we would have had our conversion right here, factor. We look at centimeter cube, so we know that the centimeter cube should be as our denominator, and our 0.0025 moles. And so centimeter cancels centimeter cube, leaving our answer in moles. But remember, it's concentration, so it's moles per dm cube. So again, this times 1000, so it's really 2.5 divided by 14.7. And what is that?
Yeah, 17.
So 0 point 0.17 moles per dm. It's gonna give me a problem. So let me write it back right here. Remember, we can express moles concentration using. So if you see 0.17, you can see it with a capital M. Capital M means moles concentration as well. Or you can see 0.17 moles dm cube with the -3. So if you're writing it 0.17 moles per, with the slash dm, we don't have to put the -3. We have the dm cube. So either way you want to write it is acceptable. So whenever you see this, capital M for moles, it is, well, capital M, it's representing molar concentration. So you can look out for that. If you use the mole dm cube, you have to put the negative sign. If you say moles per dm cube, you don't have to utilize that -3. Now, again, so now we know moles, so this is moles concentration, which means this is how many moles that is in 1000 centimeter cube. And they're now asking us for mass concentration. Whenever you're moving from moles to mass, you must take into consideration 3 things. Either it's atomic mass, formula mass, or molecular mass. Sulfuric acid, we can treat it like a ionic compound. Technically, it has the ions, the hydrogen and the sulfate ions, right? And so we know it is 1 mole, which would be equal to the formula mass. Now, if you have this, again, the question provided this. Must be a reason why they're giving you the atomic masses of the hydrogen, the oxygen, and the sulfur. So if you finish a question and you didn't use this information, maybe something is wrong. So again, you have to remember the formula. It would have been H2SO4. So it's 2 hydrogen. Each hydrogen is 1. So that gives us the 2 gram. 1 sulfur. Each sulfur. 32. And then, of course, oxygen, which is 4 times 16. How much is that again? 48?
Mm-hmm.
And so 2 and 48 gives us 50.
Wait, no. Wait, is it 16 times 4?
Yeah.
64.
How much?
That's 64,
Oh,
sorry.
64. Thanks.
Mm-hmm.
So 64 plus 32 plus 2. So that's like 34.
That's like
96.
98.
90.
Oh?
98.
Yes.
So 98 grams. So we know when we have 1 mole of sulfuric acid, it should have a mass of 98 grams. But we didn't have 1 mole. Again, we have our conversion. We have 0.17 moles. And we said that we're going to be multiplying that. And again, we know that any unit that is here, we put that as a denominator. So 1 mole over 98 gram. Mole cancel mole. And it did ask us for grams. And since we're dealing with how much is in 1,000, that is mass concentration. So 0.17 times 98 gives us
16.66.
and so we would be working with grams per dm cube. If you want to write it, and so that would have been the mass concentration. So we want to give a shout out again to D&J Document Center, one of our sponsors. We want to talk about elite detailing. Also, we want to make mention about Evergraphics Photo Studio. So you can like and share, can comment. Remember to subscribe. Mr. Thomas is the name. Buckle Down Tutoring Services.